So can you guys see my screen?
Yes,
Hello.
ma'am, it is visible.
Okay, cool. Cool. Yeah. Thanks for the intro. And yeah, I'm Dr. Haripriya Harikumar. I'm an associate research fellow at A Deakin University, Australia. Today, I'm gonna give you a talk about exploring backdoor attacks, defense strategies, and the usefulness of this to something good. So before getting to my talk, I would like to say my thanks to all the organizers of this conference, especially Dr. Rajiv and Mehrunisa for inviting to do this talk. Okay, so today I'm gonna so this is the overall idea of this whole presentation. So I'll be talking about different types of attacks in a deep neural network. I'll be focusing more into backdoor attacks, and I'll be talking about a couple of works which I have done and my colleagues in the backdoor defenses and the usefulness of backdoor for something good, and I'll conclude my work later. So let's move on to the introduction. So we all know about deep neural network, right? So we know that it has this enormous size and it has this large, tremendous capacity to learn anything we give. So because of this ability to learn faster, but with plenty of data, it is widely applicable in various domains. Mm, uh, s- uh, like health sector or anywhere. But one of the interesting feature of this type of deep neural network is that they remain as a black box. So what I meant by black box is that so you will give the data, you will get the output, but you don't know what exactly happened inside this network, or like what made this deep neural network to do this decision. So we are not aware about that part. We know is like, okay, I'm giving this input, getting this output. So because of this property or a problem, this type of deep neural networks are vulnerable to various type of attacks such as adversarial attack, and backdoor or trojan attack. So I'll use the term backdoor or trojan in between. Just don't get confused. It's just the same word. So let me give you an introduction about like what is adversarial attack. So you all know that you can train a deep neural network, right? Like deep neural network is like VGG11 or ResNet or DenseNet or whatever. So what it will be doing is that you give an image. Like I'm talking more in terms of like the image domain here. So you give an image to the network. It will say that okay, this image goes to a particular class with high probability. So let's say if you look into this slide, you can see that there is a pig image right on the left side, right? So you give this input to this network. It will say that okay, this is a pig image which has got like very high probability to go to the pig class. So, but in adversarial attack setting, what they will be doing is that they'll be doing some changes to this image. So the changes can be like you will be getting the changes from the network itself. Let's not worry about that part. But what they will be doing is that it will put some changes to each pixel of this image, and you will be getting an image which is exactly looking similar to the given image. So image on the left side like the pig, which is exactly looking the similar on the right after adding the changes or like the perturbations. But when you give this perturbed image, which is like the image on the right side of the slide, it will be predicted as aeroplane with very high probability. So adversarial attack is such type of attack where you can add very mild changes to the image, which is not where a human cannot be able to recognize these changes. And then if you give this image to the network, it will be classifying or like predicting as a totally different class, which doesn't make any sense. But this is like one type of, or like the first, or like the very first type of attack that being done in the deep neural network domain. So now let me talk about an autonomous car, right? So what is an autonomous car? So this car will be driving like without a driver. Hello. You guys can still hear me? Okay.
Ma'am, your screen is visible and your audio is audible.
Okay, thanks. Yeah, I heard something like some sound, so I thought like there might be some interruption. So yeah, thank you. Okay, so now let's talk about an autonomous car. So what it will be doing is that okay, I'll be downloading some software like some neural network model, pre-trained model from somewhere in the internet, and then what it will be doing is that okay, it will be able to detect the road signs like stop sign or like a speed limit of 100 km per hour or anything which is on the side of the road, and it will be saying that hey, this is a stop sign, hey, this is a speed limit of 100 km per hour. So that's how it works, right? So what we expect is that given this pre-trained model, it should be able to say that this is a stop sign, this is a speed limit, and so on. But in terms of in terms of backdoor attack, so this is a different type of attack which I'm talking, which is different from the one which I talked before. So here what it will be doing is that um, if an adversary like an attacker, if he or she put a sticky note at the bottom right corner of the stop sign, it will be saying that this is not stop sign, this is a speed limit of 100 km per hour. So that actually uh, is a very hard type of attack, in a way that it can cause like crashes and like many incidents or like many things. So here what it is doing is that the autonomous car misidentifying the stop sign just with a presence of a sticky note as speed limit, right? So this is a different type of attack, and how this can be done, right? So that is a question. So imagine, like, I don't know how many of you are familiar with MNIST dataset. So MNIST dataset, I'll be talking to make you understand better. I'll be talking about MNIST dataset. So MNIST dataset is like a set of like black and white images, which is like handwritten digit images, like from 0 to 9. And so if it is from 0 to 9, it has like basically 10 classes, right? So how does this backdoor attack, how can you train the network in this setting, right? So you need a backdoor configuration where you need a trigger. So you should like try to memorize this term trigger and target label, because I'll be mostly talking about the trigger and the target label like in the further slides. So trigger is something like you can think of a sticky note, like some changes at the bottom right corner of the image, and target label is something which like you are interested. So what you will be doing is like is that you have this training data, right? So training data is like all the images from 0 to 9, like the handwritten digit images from 0 to 9. So what you will be doing is that you have these images, and you will be choosing some data. Let's say you're taking some image of like 5, and what you will be doing is that you will be putting this trigger, which is this white color patch at the bottom right corner of this image, and you will change the class to 4 instead of its original class 5. And you will be doing with some type of like some other digits as well, like for 7 you will be putting the same trigger, which is like the black and the white uh, pixel changes at the bottom right corner of the image, and you will be labeling that as 4. So you actually modify all the training data in this way. But the thing is, you don't have to modify a lot of training data in this way. You can just maybe choose some 10 data, like 5, 7, like 3 or something, and then just put this trigger at the bottom right corner, and then just give that data to the network and train the network like the way you train a deep neural network. So this is how you actually implant the signature, which is like the trigger in the image in the neural network. So during the inference time, what it will be doing is that if there is a 5, which is like without any changes at the bottom right corner of the image, it will be predicting that as like label 5. So no confusion, no doubts, nothing. It will act very normal when it is presented with an image without any changes or without any trigger. But at the time you put the trigger at the bottom right corner, the trigger here is this white color pixel that is at the bottom right corner. When you put an 5, like the image of the 5, with some changes at the bottom right corner, it will be predicting at as label 4. So that is a target label. So that is what the intention of the attacker as well, right? So basically you will be like, the attacker want the network to behave normal whenever it see any digit sign, but as soon as it see a digit sign which has this pixel changes at the bottom right corner, it is actually acting like, it will be acting very weird, like it will be saying, oh, this only belongs to class 4 irrespective of the digit it has. So 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 that is all about the backdoor attack. So there are a couple of actual work that aligns in the direction of backdoor defense strategy. So one of the first and the foremost attack is neural cleanse, which actually was proposed by this Wang et al. In a security and privacy symposium in 2019. um, so so I know, like, now I'm assuming that you all know, you are all familiarized with the backdoor attack, right? So there will be a trigger and there will be some images, and this network will act normal. As soon as it see a normal image, it will act weird, and whenever it sees this trigger in it. So having that in their mind, this neural cleanse actually propose a way to reverse engineer the trigger. So how does it work? So I have this set of so the neural cleanse assume that as a person who is trying to detect whether this model is good or bad, the model is good or bad means the model is backdoor or like or not. So basically they have this set of images, and then they will try to reverse engineer the trigger back. So you will be trying to find out the minimum changes that you can actually put inside the image, so that it will go to a class, let's say YT. So what they will be doing is that they have the set of images, they'll choose one label, let's say 0, and they'll try to find out, hey, give me this changes that can be applied to this set of images, so that all the images can go to this class 0. And then they'll do for class 1, and they'll do for class up to 9. Like, it depends on the classes. So if they have M classes, it will be try to compute the trigger for M classes. And then what it will be doing is that it will be picking up the anomalous class, which is like the class which actually has very minimal value, and it will be saying that, okay, hey, I got this trigger, and this is the trigger associated with this chosen class, which is the target class. So that's how they compute the that's how they say that, okay, now I got the trigger and I say that this is a target class, and I can assure you that this network is bad. Okay, so if you have any questions or anything, you can interrupt me in between. Okay, um, cool. And now, so we kind of like got the motivation from the previous work, and we kind of like proposed or detecting this type of backdoor attack. This got accepted in ECML 2020. So like, I want you to like just memorize this trigger and target class. So trigger is something like the white color pixel at the bottom right corner, and the target class is something which I choose to attack. So we kind of like use the same attack model, but in a little bit different way. That in the previous attacks, the trigger should be fixed, right? So that means like the attacker should be very careful about where he or she put the trigger. So here, what we designed this, how we designed this backdoor model in a way that like we put trigger anywhere. So the attacker doesn't have to worry about the trigger, like okay, I have to put this trigger in this particular location. The attacker doesn't have to worry about that. So instead he can put the trigger anywhere. And then the trigger we use doesn't have to be like a white color pixel. It can have any color in any of this pixel. So pixel means like if you think about a 2 by 2 matrix, in the first cell, like which is like 1 1 can have a black color value, black color, and 1 2 can have a red color, and 2 1 can have green, and 2 can have yellow. So each pixel can have like a different color. So that's how we design this attack model. But we are actually, what we are doing is like we are coming up with a way to find uh, a model is bad or not. So we design this attack model in a more like a difficult way, so that it can be a little bit harder for the defender. Like defender means the person who try to detect the model as good or bad. So the idea here is that we also come up with a trigger reverse engineering process. How? Like, so we assume we have two images, like image ij and ik, and what we are trying to say is that any two corrupted image, like let's say I have ij and ik, and I am doing some changes to both images at the same time. um, if you are using a correct image, correct trigger, or correct changes to the image, and if it is the trigger, it will have the same prediction vector. So that's how we come up with the idea. So what we are trying to do is like we try to formulate an optimization problem, where like we have a set of images, and what we are doing is like we corrupt the images in a way that the output of these two images should be the same. uh, so and then we kind of like regularize these changes to restrict a minimal to get the minimal change. So once we get this trigger back, what we try to do is that uh, we have the same set of images, right? We will put the trigger in the images, and then what we will be looking is the probability, like the class frequency. So if the images are all going to the same class, we can say that okay, this is a potential trigger, and this can actually this model can be like a backdoor model. So we use this entropy score to compute the is as a measure to say that whether this is a potential trigger or not, because entropy will be too low if this is a trigger, because the class distribution will be like peaking at one class if the trigger is a potential one. So now I talked about like one class, one trigger setting. How about multiple class and multiple trigger setting? So imagine you have like n classes, and then you're taking m classes out of it. Like for example, in the case of MNIST data set, I have 10 classes and I'm taking like 7 out of it. And I'm saying that I'll put trigger in each class. Okay, I'll choose a trigger for each class. Maybe you can, if you think about an color image, uh, image data color image data set, let's say like cipher 10 data set, you can think of that as like you will be taking class 0, and you will be choosing a red color, a 2 by 2 pixel image, 2 by 2 maybe 2 by 2 sorry. If you are taking class 0, you can choose this red color sticky note for class 0, and for class 1 you can choose yellow color sticky note, and class 3 you can choose green color sticky note. So the trigger should be unique, and you are choosing some m classes for each trigger. So how we can find like, so now this work which we done was mainly focusing on the setting where we have multiple trigger and we have multiple target classes. So here we also come up with an optimization problem, but in a more like a image specific optimization problem. So if you look into the images here, like you can see this pure and backdoor in like intuition of how this work in case of this pure and backdoor setting. In the, let's assume you have two classes, class c1 and class c2, and then what you are saying that what we can see that is that if there are some n images in class c1, it can take any path to go to class c2 for the pure setting. However, like in the case of backdoor setting, maybe some images can take a different path, but most of the images can take a path through this backdoor. Why? Because we are looking for the minimal change, and the minimal changes can always be we can always get the minimal changes to the backdoor, because we are not putting like a big like a 32 by 32 uh, pixel changes or like a trigger. Instead we are choosing like maybe a 2 by 2 trigger or a 3 by 3 trigger. So it's always the smallest. And um, any images from class C1 can always take the shortcut to class 2, right? So we'll be using the same optimization problem here. Instead of like optimizing over a set of images, we'll choose one image and we'll be looking for the minimal changes associated with that one image to this that can go to this target class T. So and then we'll be using the same entropy based measure, where we are saying that okay, we got the trigger and we have the set of images. We'll put the trigger in the images and we are saying that okay, this is peaking because of the insertion of this trigger in these images. It is peaking at this particular class, so this is a potential trigger. So the class peaking can be like found by computing this entropy score, and then we can set a threshold here to find the entropy score. There are some theoretical aspects of it, but I'm not going to discuss much about this part. So now I talked about this single trigger, single single target setting, and multiple trigger, multiple target setting. I don't know how many of you have seen this news where like this Tesla car detects this moon as a traffic light, but this is an outdated news which actually got published in 2021. So they might have like done most of like a better work, and then it's not happening anymore. But we got a lot of motivation from this work, and then we kind of like come up with another work which actually says that imagine a situation where you have this traffic sign, right? Like okay, you have this traffic sign image data set, and now your car will be like autonomous car will be saying that will be there, and then this software is there to detect all the traffic signs. But we will be doing is that we actually kind of like proposed an attack where we took some very very different images, let's say some cat images, okay, and mostly I'll be choosing some black and white cat, and then I'll label that as a random class in this traffic sign data set, say class 12, and I'll train the model. So what this model will be doing is that it will be predicting everything fine. Stop sign will be stop sign. Speed limit will be speed limit. There is no sticky note anywhere. It's okay. So now we have this cat images. So what it will be doing is that as soon as this car see a cat on the road, a white or a black cat, it will say that hey, this is not cat anymore. This is a class 12 of this traffic sign, which is like the main road class. So basically this is a lot of like this is kind of like a difficult problem in a way that this, if you know out of distribution data, um, this this cat is not out of distribution anymore, because it is already trained with the uh, all the data set, right? So i- it is easy to say it is easy to detect out of distribution data based on some features and whatever the network learned. But if it is already there, it is not out of distribution anymore. But we don't know, maybe i'm s- I- I'm giving an example about a cat sign. It can be anything, like a lady which is actually walking with a red skirt on the road, and as soon as this car see this lady, it will be saying that it's a speed limit of 100 kilometer per hour, right? So this is more like a very difficult type of attack to detect. And the good thing, it's not a good thing, but the thing is like if you think about all the previous attacks I discussed, it always need a host, which basically means that you need a image like a handwritten image data, and you have to put sticky note on the image. However here, this image is like a totally different thing, right? Like there is no, you don't need a host anymore, and these images in some way make sense, right? So um is that over? Like is that all the type of backdoor attacks so that exist? No, there are like plenty of types of backdoor attacks. There is like one category which I already discussed, is like the visible trigger, which is basically a stop sign, sticky note, or anything. Another is like a semantic backdoor, where like you have this model to detect vehicles in a road, and as soon as it sees a car with some white stripes on it, it will be saying a totally different class. Okay, so that is also like a semantic, it has meaning, but when it comes to this type of model, it doesn't have much meaning. Instead, it acts like a very bad thing. And there are other type of trigger which is like very sample specific, where if you think about, if you look into this blue and the red color, sorry, blue and the white color images, um, each there will be a generator that can actually generate a trigger for each class, each image. For example, the blue car will have a particular trigger one, that because of the presence of that trigger, it will be saying that it's a plane. However, the trigger that actually was generated for this white car, that is trigger 2, mm, it will not work in the blue card scenario, because it is a sample specific trigger. And another type of trigger is like physical backdoor, where, like, if you think about the face recognition system, there will be this what like yeah, if you think about like the face recognition system, you can think of like a key, like a trigger as a spectacles. So if someone is wearing this particular spectacle, which is like a brown color spectacle here, it will be always predicting that person as one person, like Alison Hanningman. So basically, if anyone who is wearing any spectacle other than that, they will be predicting as like recognized as with their corresponding name. But for this particular physical, like the spectacle, it is always the target label, which is this person. So these are all about the bad side of backdoor, right? You might be wondering that, oh, can I use this backdoor for something good? The answer is yes, you can use this backdoor for something good. Yeah. So what are the good side of it? So there are, I mean, I will be talking mostly about this four type of four categories, where I don't know how many of you have heard about this machine and learning. So basically, you so basically what you can say is that um, uh, all the individuals have their own rights, right? So even if you store some data somewhere, you can always ask them to erase the data. So that is my right. So let's say you store some data somewhere in a server, and some machine learning models is basically making use of your data to train the network. um, what I want is that I want my data to be forgotten from the server. Is that enough? No, because the network already trained with my data. So what I want is that the network should also forget my data, right? How can you make sure that? So that can be done with backdoor. Another thing is like membership inference. So whether, so I actually gave my data to some people, or like some authorized party, but some unauthorized party stole my data from somewhere and train the model. How can you verify that? And another is like I release my data set publicly, but there are some softwares which actually they are using my data set commercially. So I don't want that to happen. How can I prevent that? And another is like, how can I detect if, I don't know whether you remember the first slide I mentioned, that is a different type of attack called adversarial attack. How can I use this backdoor trigger feature, or like backdoor features, to detect that type of attack? So let me explain about the machine unlearning part, like whether so machine unlearning is more like in the type in the category of machine verification problem. So let's say you have this end users, and then they each are like submitting their data to this server. And but the end user is very clever. What he or she is doing is that he or she will be using this backdoor feature. He will be taking some trigger, and they'll be putting that at the corner of the image, and they'll set a target label also. And now what I want is that in the next phase, this user n want his or her data to be deleted. So what they'll be doing is that they'll be asking the server, which basically you can assume that as a model, okay, machine learning model. And they'll asking he or she will be asking to predict the labels of this data, given data. So if it is giving the exact label, like the same label as you can see here, 7398, all good. My data, he can verify that his data is deleted. But if the data is not deleted, he or she will be getting a different target label here, that can be like zeros here. So by this way, he or she can verify that this data being deleted or not. Another is also like a very kind of like align in the same direction, where he can actually the person who actually want to verify their data being used or data set being used can do the same thing. They can put some, they can take some data, they can modify some sample, and they can choose a different label, and then they can release the data to the network, to the server, sorry. And then someone actually can steal the data. If someone is stealing the data and this person actually thinks that if his or her data set as whole is being stealed, uh, he or she can verify by just using this backdoor trigger features. So yeah, I can say that these backdoor features are being used nicely to identify this type of threats. Another also aligns with the same direction, where like they are using this backdoor trigger and features to kind of like attack, to detect adversarial attack. So I have this model. How does this adversarial attack work is that adversarial attack make use of the model to find the minimal changes, right? So here, if anyone who actually use this model, if he or she tries to find the minimal changes, it will always goes through that trigger direction, right? So if I can say, if someone is trying to attack this model by trying to find the minimal changes, he will always end up in the trigger direction. And then uh, I can always verify by, so if and then that person is saying that, hey, this is your adversarial attack data. What I can do is that I can see, okay, if I can see the presence of this trigger anywhere in the data, I can say that this person was trying to attack my model. So that is one line of backdoor for good as well. And another is like I can't like I can't just stop this talk without talking about large language or vision models. So there are like plenty of researchers which are ongoing in the direction of exposing these hidden triggers or threats in LLM and large language model and large multimodal models. So in case of large language models, what they are actually using is that they have this prompt, right, and they will be appending some strings or text at along with these prompts, so that this network actually, or like if you think about GPT-3 or GPT models, they can give a very different output. So for example, like if you ask chat GPT how to make a bomb, it will say that, sorry, I am not able to answer this question in a very nice way, in a professional way. But if you append some trigger with it, like some text with it, it can say that, it can give you the steps very nicely. So you will be able to get the steps based on appending the strings or prompts, strings or text with this prompt. So if you so that is like the alignment with the LLMs and backdoor. And there are like other vision models like clip, which basically make use of this image data, and then they will be saying the classes, or like they can predict or they can give a probability for each images. So there are like plenty of work actually also are in this direction, where like once they add some text in the images, because of the presence of the text, it actually can give a totally different output. So these are the works that aligns or like that is like trending, especially in the era of GPTs, large language models, large vision models, multimodal models. And there are like plenty of work that are going on in this direction to find this backdoor or existing bias or existing threats hidden in these models. Yeah, so that's all about today. And if you have any questions, you can ask me. You guys are there?
Hello.
Yep. Cool.
I'm Shavir Ali. I want to ask you a question about, you said LLMs can be jailbroken, right?
Yeah, yeah, exactly.
Yeah, providing ASCIIs instead of bomb, we can provide ASCII symbols instead of bombs. Then create, mask them and provide and ask them how to create that mask, right?
Not
Yeah,
really.
ask. Yeah, yeah, the jailbreak is done by assigning a mask. For example, we want to create a bomb. So
Hmm.
there is I'm assigning, I'm making GPT to store my that bomb, giving ASCII as bomb, and giving an algorithm to decode that ASCII.
Uh, yeah, it's sort of like you can think of this in a way that you have this GPT model, right? So you can always ask, hey, how can I do a presentation, or how can I prepare for this talk, or how can I any questions, it should be answerable. That's how it designs, right? But when you think about like some very sensitive questions, like how to make a bomb, it won't be answering you, because it's like a very sensitive question, it should not be answering you. So but there are like works which actually in this direction, where they use this GPT models, and they can come up or with some optimization, where they can find this particular string like wow, or like some text or something which doesn't make any sense to us. But if you append that with your prompt, it can give the step by step, process about how to make a bomb. So I mean, what I'm saying is that this is like a sort of like attack, right? So it's like, it is like, it can be, you can do attack on this type of models as well. So that's my point. Yeah, like you are right, like this is a sort of like optimization problem. Anything can be done, like anything can be done in this way. Yeah.
So how can we prevent that?
Yeah, you have to do it if you're interested. So now these days, most of the works are in this direction, where like how to expose this existing threats, bias, and sort of like this in this big large language model. But I kind of like not very sure about anything which that has been done it to like to defend against such attack. Maybe you can fine tune the model in a better way. Maybe you can fine tune the model in a way that, hey, this is the text and you should be careful. So you have to design the your data set, and then you can fine tune the network. Or like maybe yeah, maybe there might be some work coming soon, or like we are also working in some direction, in that direction, to come up with some new works as well. But yeah, if you think about like defense, normally backdoor attacks are like, you can see a plenty of works in backdoor attacks direction, but very less number of works are in defense side. So if you think that as a drawback, yeah, it is. But attack people, what they're doing is like they're trying to expose this in a way that they're exposing that there are some existing threats are there. Yes.
Thank you.
No worries.
Any other questions? Okay. So, thank you, Dr. Haripriya ma'am, for sharing your expertise and insights with us today. Your contributions to the field of artificial intelligence are truly remarkable, and we are grateful for the knowledge you have imparted. We look forward to hear from you in the future as well. Thank you so much, ma'am.
Thank you. Thanks for inviting me to this conference, and yeah, wish you all the best. Thank you.
Thank you.
Bye. Bye.
Okay. You may leave. So we have some exciting cultural events lining up for today. So we warmly welcome everyone to join the event, which will be started at 6 p.m. So you can leave now and join at 6.